The second lesson is going to cover a lot of definitions as well, covering geometric terms. And we're going to start by introducing some simple terms, moving into polygons, different kinds of polygons, and then specifically focusing more so on triangles and quadrilaterals. So our first definition is a geometric definition for a curve. By definition, it's anything that can be drawn without lifting the pencil and without retracing any part of the path except single points. And so if you look at some illustrations, these are all illustrations of curves because all of these can be drawn without lifting the pencil and without tracing any part of the path except single points. And I want to point that out right here. If we started drawing this and we came down here, over here, we would, we would cross over, and that's okay. Coming down, cross over again, that's okay. But we haven't retraced anything. We do meet back up here in this corner at a single point, which is okay by definition. Same with this triangle. You know, if you draw here a line, up a line, down a line, we get back to this vertex point, but that is at a single point. And so there's a lot of different, you could draw, an infinite number of different types of curves, but it's basically any figure or anything you can draw without lifting your pencil and without retracing any part of the path except for at a single point. Now, a simple curve gets a little bit more specific. It's still a curve, but is a curve that doesn't cross itself except at the starting point and the stopping point. Those can be the same. So right here, that would throw this one out because it does, cross over itself right here. So this would not be a simple curve. Whereas these other two up here in the top curve definition would also be simple curves. But right here, we have different simple curves. Notice that these are all curves. They can be drawn without lifting the pencil. But they do not cross over themselves except for at the starting point and the stopping point. Those 2 points can be the same. Now, a closed curve specifically is a curve that can be drawn by starting and stopping at the same point. So up here, this would be a closed curve. This would be a closed curve. This would be a closed curve, but right here, this would not be a closed curve because you do not start and stop at the same point. So I'm giving you some images of that. Here we have the same, follows into the definition of a curve, but it's closed because if you were to draw it on all three of these, you would start and stop at the same point. Now, when we get to the definition of a polygon, they're all simple curves and closed curves, but now all of the sides have to be segments, and we know segments are straight. And so we can see some visuals of polygons, and we're going to go into the different kinds of polygons, which we've all learned those names: octagon, heptagon, hexagon, pentagon. But a polygon, by definition, is when we have a curve, which is something that can be drawn without lifting your pencil and without any retracing. It's a simple curve in that it doesn't cross itself. It's a closed curve in that it can be drawn by starting and stopping at the same point. So a polygon falls into all of those. And so if we look, here at this shape is a polygon. It's also a closed curve, a simple curve, and a curve. It fits all of those definitions that we've gone over so far. And this one does as well, because we can see on both of these, all of the sides are segments, and then it follows all three of these previous definitions. A vertex is a point where any two sides of your polygon meet. So we have a side and a side, but where two sides meet up, that would be a vertex point. And so this specific polygon here has a vertex here. So we have a vertex here, and here, and here, and here, and here we have, multiple vertices. Any point where two segments or two sides of the polygon come together. Now, two more definitions on this first page. And I hope these are all, review for you. But we have convex curve and concave curve. So those are definitions, that you learn when you're learning geometry throughout your K through 12 years. So a convex curve is a simple closed curve. So it meets all of those definitions of a simple closed curve in which the segment connecting any 2 points that are on the curve is wholly contained in the interior. And so I'm kind of giving you a visual of that. If you were to draw, here's a visual of that. If you were to draw a segment connecting any 2 points that are on the sides, that entire segment would be on the interior. And any segment that I draw inside of this, from one point to another point on the edge, there's no way I can draw a segment connecting any 2 points that are on the sides of this that's not on the interior. Same here with this circle. If I were to draw a segment anywhere going from the edge to the edge, the entire segment would be on the interior, wholly on the interior, and that's a convex. Concave is still a simple closed curve, but it's where it's possible that you can draw a segment where the 2 endpoints of the segment are on the side of the concave curve, and it can be on the exterior. So it's a simple closed curve in which a segment connecting 2 points may be drawn such that it's not wholly contained in the interior. And so here I can draw segments inside of here that are completely on the interior, but you can see right here I was able to draw one that was on the exterior, and same right here. I can still draw some that are wholly in the interior, but I can also draw some that go on the exterior of this curve, making this concave. And you'll notice that happens when there is this caving in part of your curve, and that's why it's able to do that. And that's why it's called concave, because you'll notice here it caves in right here, and here it caves in right here, and that's why why we're able to draw those segments that go on the exterior. So the next thing we're going to do is we're going to look at just a variety of different shapes. You'll have to do this on your assignment and on your exam as well. And we're going to go through and we're going to identify all of the figures that meet the definitions that we've gone over in the previous page. So the first thing we're going to talk about is, out of these 8 shapes, which of the 8 fall into the definition of a simple closed curve? Which ones are polygons, which ones are convex, and which ones are concave? Okay, so let's go through and first identify all of the simple closed curves. And you can refer back to those definitions on the first page as much as you need to. So remember, a simple closed curve is a curve, so something that can be drawn without lifting your pencil, without retracing any parts. It has to start and stop at the same point, and it cannot cross over itself. And so if you look at number one does fall under all of those conditions. You can draw it without lifting your pencil. It does not cross over itself, and it would start and stop at the same point. Now, number 2 does not. If we were going to draw that interior rectangle there, we would have to lift your pencil or your pen, whatever you're drawing with. So that is not a simple closed curve. Number 3 would be, because we can draw that without lifting our pencil. It would be drawn by starting and stopping at the same point, and it does not cross over itself. Number 4 would be as well, for all of those reasons that I just discussed. So would number 5. You can draw that without lifting your pencil. It does not cross over itself. You would start and stop at the same point. Number 6 would not, because the gaps here would indicate that you had to lift your pencil, and so that would not work. Number 7 would. You can draw that without lifting your pencil. You would start and stop at the same point, and it does not cross over itself. Number 8 is not, because if you were drawing this, okay, we're not lifting our pencil, but we already hit a point where we started and we're not finished. And so over here, same thing, as we go around here, we come back, but we didn't start and stop at the same point. And so that's why that's not a simple closed curve. Now, by definition, a polygon is simple closed curves, so it has to be out of the ones we just listed, but the sides have to be segments. The sides have to be straight. So 1 would be a polygon because it's a simple closed curve with the sides that are segments. So would number 3, and so would number 4, and so would number 5, because all of those are in our list of simple closed curves, but the sides are straight. The sides are segments. Now, out of those polygons, because I want convex and concave polygons, so I'm looking at 1, 3, 4, and 5, and I'm identifying which ones are convex and which ones are concave. So convex, the only one that would be convex would be number 5, because any segment that you draw connecting points on the edge, the entire segment would be completely inside of this polygon. But over here on number 1, if I were going to draw, connect 2 points that are on the polygon, I can go on the exterior, and that makes that concave. I could also do that here on number 3 and as well on number 4. It's possible to draw segments connecting the sides that's on the exterior. So that's just kind of a fun way of making sure your students know those definitions. So this is something, you could do as a walk around or a scavenger hunt around the class, where you have these different shapes posted around your classroom, and you could go and have your students, list all of the names, out of all of these, which ones are polygons or convex or concave. So there's a bunch of ways that you could make this fun and engaging. Okay, in this video, I'm going to go over just a few more definitions, and then we will stop this one and go on to the second video. So lots of definitions again, and you will have a bit of a smaller project within this lesson. You're going to create a Piktochart, and there are going to be definitions that you can choose from. So I'm just kind of warning you of that in advance so that you take note of all of these definitions. So first definition, an interior angle, an angle of the polygon. It's formed by any 2 sides of the polygon having a common vertex. And so it's any angle basically that's on the interior of the polygon. So notice this angle here. When the sides of the angle are also sides of the polygon, it creates an angle here that's within the interior of the polygon. In comparison to an exterior angle of a convex polygon. And that's important that you note that it's convex, it's not concave. So what this is, it's determined by any side of the polygon with the extension of an adjacent side of the polygon. And here's what that means. What I can do is I can extend this side, and what I do is I create an angle here that where one side is a side of the polygon and the other side is the extension of another side of the polygon, creating an angle that's on the exterior. And I could do that, multiple ways. So like I could extend this side and create an angle on the exterior. I could extend this side and create an angle on the exterior. So there's multiple ways to create exterior angles of a polygon, and I could even come back and draw this way, extending this side, and create an exterior angle. But when you have an exterior angle, one side of the angle is a side of the polygon, and the other side of the angle is an extension of the adjacent side on the polygon. Okay, congruent parts. Anytime you're comparing, 2 figures or 2 polygons, if the parts are exactly the same size and exactly the same shape, basically they are identical, they are said to be congruent. And here we have the symbol for congruent. So here we have congruent segments. They are identical segments. They are exactly the same length, the exact same thickness. They are identical in every way. If you trace one line segment, you could, trace one, pick it up, put it on the other, and they're exactly the same. You could measure them, they would be exactly the same. You can use tools like your compass to draw them, and there's ways of doing that to make them congruent. Now notice the naming here. I have segment AB with the correct segment symbol above it. Segment CD, they are congruent to each other, so I have the congruency symbol. The last definition for this particular video is congruent angles. So if we have angles that are the exact same measure, and we've learned how to construct congruent angles in the previous lesson, but if they have the exact same measure, they are said to be congruent. Now here I was able to name these angles by one letter, and they don't actually visually look exactly congruent, but they are based off of the definition. They have the exact same measure. We're not going to name them with multiple letters because I didn't identify additional points on these angles. But if they are angles that have the exact same measure, they are said to be congruent. And this is angle A is congruent to angle B.